figures? Put your brain in the game.
How would you like to be called the world's greatest athlete? Pretty cool, right? Well, first you have to do all this. The 100-meter sprint, the long jump, the shot put, the high jump, the 400-meter run, the high hurdle, the discus, the pole vault, the javelin toss. And finally, there's the 1,500 meters. Whew, that's almost a mile. Since the decathlon was introduced to the Olympics in 1912, records keep getting broken. Are the athletes today stronger than they were in the old days? It might be, but there's more to it than that. Today's athletes are applying science to sports to get the most out of their bodies. What could science have to do with running and jumping? Well, for all the different events in the decathlon, they all have one thing in common. Bodies in motion. A runner's a body in motion. A discus flying through the air is a body in motion. And a pole vaulter arching over the bar is a body in motion. So if you want to understand how to use science to better your performance in track and field, you have to understand the science of motion. In order to understand motion, you have to understand the meaning of two words: speed and acceleration. You see that guy back there? That's Dan O'Brien. Dan took the gold in the '96 Olympics and is ranked #1 in the world. So I'd say he knows a thing or two about acceleration. When you fill your tax return for occupation, do you put, like, you know, world's greatest, fastest guy?
No, I'd like to, but I just put professional athlete. That's good enough for me.
So why did you choose the decathlon? I mean, you could excel at almost any sport. Why something so challenging?
I think the decathlon is kind of a contest against yourself, and that's what I really enjoy most about it.
So did you cream all the kids in high school at every sporting event?
Not all the time, because I was a pretty small kid in high school. I was just scrawny, if you can imagine me, about 5'6", 120 pounds, and a big old afro running around out there. That was me, and my parents didn't let me play football until I was in the 11th grade because I was just so small. But I got bigger and stronger, and then I started to excel. My 11th and 12th grade year, I was a good runner, good wide receiver, and I played a lot of basketball. Speed's a really important part of what you do, right? Absolutely. Of the 10 events in the decathlon, 9 of the events involve speed, and so I have to be very speed conscious. So what can you tell us about speed? Well, from a technical standpoint, speed is the measure of the rate of motion of an object. Right. Speed's simple. It measures the rate in which an object covers a distance, like a car going 40 miles per hour. That's right. If it kept going 40 miles an hour, in 1 hour it would go 40 miles. Okay, guys, how do we measure speed?
In a car, the speedometer measures it.
Yeah, but what about in the 100-meter sprint? Races are usually measured in times, right? But that doesn't tell us the runner's speed. We have to break his time down into speeds.
Couldn't we just divide the distance covered by the time it took?
In 1991, Dan O'Brien broke the current world record by running the 100 meters in 10.23 seconds. Okay, so now we have a time for a certain distance, 10.23 seconds for 100 meters, which means we can figure out average speed using the equation average speed equals distance over time. The distance we know, 100 meters. The time we know, 10.23 seconds. All we have to do is divide distance by time, and we've got an average speed of 9.77 meters per second. Speed's always measured in terms of distance and time, miles per hour, feet per second, whatever. Dan ran an average speed of 9.77 meters per second. That's this far every second.
But he wasn't really running that speed during the whole race.
What do you mean?
That was his average speed, but it took him time to get up to that speed. Maybe he slowed down or sped up towards the end of the race.
Right. So there's two types of speed. There's average, like we just did, and the other's called instantaneous. Dan's speed is going to vary during the course of the race. At the start, his speed is 0 meters per second. Then as he leaves the blocks, he goes faster and faster until he reaches top speed. Then he might slow down if he gets fatigued or speed up with a push to the finish line. So how are we going to find Dan's speed at any given instant of the race? Instantaneous speed is kind of hard to judge because you can't freeze time. A good example of instantaneous speed is a car's speedometer. It shows you your speed at any given instant. How can we find your instantaneous speed at different parts during the course of the race?
Well, what you want to do is you want to break the race down into what we call instants, which are short segments, and time them.
So if we did that, we can break it down into smaller segments and get a better look at what happened.
That's right.
Nika will run a 20-meter sprint. We'll have stopwatches along the race at every 5 meters to time each segment. We'll all start our watches at go, and we'll all stop our watches as Nika passes us. On your mark, get set, go! The first 5 meters took 1.91 seconds. At the 10-meter mark, the time was 3.1. At 15, it was 4.08, and at 20, 4.89. We can find the time each segment took by just subtracting. So we get 1.91 for the first 5 meters, 1.19 for the second 5 meters, 0.98 to run the third 5 meters, and 0.81 for the final 5. Okay, now that we've figured out the distance and time for each segment, what's next?
Well, now we can figure out speed using speed equals distance divided by time.
Right, just like we figured out the average speed for the whole race, we can figure out the average speed for each smaller segment. So we just divide 5 meters by the time it took to get how many meters per second. The first 5 meters, the average speed was 2.6 meters per second. Then for the second 5 meters, the average speed was 4.2 meters per second. The third was 5.1, and the last 5 meters was 6.17. Now we have a pretty clear picture of our run. Nika was moving faster and faster in each segment. Hi, what did I do?
Ma'am, I stopped you for doing 70 miles an hour in a 55-mile zone.
Oh, well, I couldn't have because I just left the house 5 minutes ago. Get it? 7 miles per hour, 5 minutes? Dan, we just figured out times and speeds for segments of a race.
That's right. They're called split times, and we call them splits.
Does a runner actually use splits?
All the time. You know, a runner uses splits to analyze his race and to establish some kind of pacing.
We could take Dan's split times for every 10 meters of the race. Then it'd be really simple to graph out his speeds like this. Look at what we get. He reaches top speed around the 40-meter mark. At the 90-meter mark, he slows down a bit to 10.98 meters per second. He was slowing down between 80 and 90 meters. Then he put on a burst for the final 10. So what can we tell about Dan's speed from our analysis of the 100-meter sprint?
He was going faster and faster.
And what does it mean when an object goes faster and faster?
He was accelerating.
Exactly right. Acceleration. Anytime we change our speed, we're accelerating. Faster, that's positive acceleration. Slower, that's negative acceleration. We always talk about acceleration in terms of time. Acceleration is the rate of change of speed. How long something takes to change speed. Look at the first 40 meters of Dan's race. He was accelerating, and we can figure out his rate of acceleration. Dan accelerated to his top speed of 11.36 meters per second at about 40 meters. To figure out his average rate of acceleration, all we have to do is take the change in speed, 0 to 11.36 meters per second, and divide it by the time it took, like this. Acceleration equals change in speed over time interval. Simple. How do we figure out at what rate Dan's speed changed from 0 to 40 meters?
His change in speed was 0 to 11.36 meters per second, so it's 11.36 meters per second.
Just divide that by 4.91 because that's how long it took, and you will find his average acceleration.
That's 2.3.
Yeah, but 2.3 what? Hey, Dan, we figured out your average acceleration is 2.3, but 2.3 what?
You divided speed by time, right? All right, so here's what you got. Your speed was meters per second, and your time was in seconds. So your answer is meters per second per second.
What that means is Dan's speed increased by 2.3 meters per second for every second he ran. You can think of it like this. At the end of Dan's first second, he was traveling at a speed of 2.3 meters per second. At the end of his next second, he'd be going 4.6 meters per second. He adds another 2.3 meters for every second he runs. Whenever we talk about acceleration, we talk about it in distance per second, or we can say per second squared. So what help would seeing a chart of your acceleration be to a runner?
Well, they would know their strengths and weaknesses. If they didn't get a very good start, they would know that they would need to accelerate faster later. And if they were a fast accelerator, they would need to know that they can't slow down later because somebody may be coming on later in the race.
So how fast is Dan's 2.3 meters per second squared? Well, that's 7.55 feet per second squared. How fast is that? Well, it's about the same acceleration as a commercial jet taking off. A jet accelerates at 7.3 feet per second squared, or almost as fast as a car that goes 0 to 60 in 10 seconds, accelerating at 8.8 feet per second squared. So that's pretty fast. I can get this car 0 to 60 in 3 seconds. Just drop something and it accelerates at a rate of 32 feet per second squared. Now that's fast. Okay, so what did we learn?
The speed is a function of distance and time.
That you can break down average speed to find instantaneous speed.
And you can also measure speed by stride, frequency, and length.
And acceleration defines the change in speed over time.
Right! I'd like to thank Dan O'Brien, Rick Sloan, the students at LDville High School, Rob, Nathan, Tia, Nika, Leroy at the HEG Athletic Complex for helping us out today with ESPN Sports Figures Tracking Speed.